Okay, now here's again is our integral for the field. I've gone ahead and filled in the parentheses down here, so you can have that for reference. Now we want to, there's a simpler way to construct the integral for the field, and it's a simpler integral. And what's going to actually happen is the integral is going to be equivalent to what happens if we cross out the y and j components up here. And that's going to leave us with a pretty simple change of variable and then a trigonometric substitution, which will allow us to do the integral pretty easily. Now, let's go up here. Now, what I want to do is I want to isolate a point x, and I'm going to kind of erase the x, y, z up here, because that would imply x here and x here. So we'll get rid of that because we've already done that. For a given point x, a cross-section of this cylinder perpendicular to the x-axis is going to be a circle, and it's going to be this circle, and we've already seen that. So we take that circle and we represent it up here. Here's the x-axis, here's the circle. We're looking at it from some perspective over about here. Okay, we take a point, any point within the circle at position x on the axis. We have any point within that circle, let's say any point is going to be at some distance r star from the x-axis, and that might be purely in the y direction, might be in the y and the z direction. It doesn't, as we'll see, it doesn't matter. Now we have this point. We're going to have an r vector here, and I haven't labeled the r vector. And again, the r vector has nothing to do with r star. R star is just the distance to this point, wherever this point is. And notice I haven't given it y and z coordinates. It does have coordinate x, and it has some arbitrary y and z coordinate to put it at distance r star from the axis. So we'd have an r vector here, and we have then a delta g gravitational field vector back toward this point that would indicate the acceleration of any mass that we would put at this point due to the mass in the vicinity of this point. So, okay, we've got a point. We can think of some little region around the point, some little region around this point. So that region has a mass that gives you a contribution to gravitational field here, and that contribution will be the delta G that I've labeled here. Now we take another point, symmetric with this point about the x-axis. In other words, we just go from this point right through the x-axis in equal distance on the other side, and we get this point. And then we have our symmetry. So we have now 2 points symmetric with respect to the x-axis, some region around this point, and that's going to result in a gravitational field here. And we also want to have equal volumes. I guess I better put that down. Equal volumes here and down here. The main point of this symmetry then, and I'm not sure the labeling of equal volumes came through, there we go. The symmetry that we have between these 2 points implies that these vectors are going to be symmetric about the x-axis. A very simple symmetry argument. So the field contributions due to these 2 volume increments, are going to be symmetric with respect to the x-axis. Now, if we draw those 2 field contributions, we can find the resultant of the 2. One way to find the resultant is just take this vector and put it head to tail with this vector. Clearly, we come back to the x-axis, showing that the net contribution of these 2 volume increments is in the x direction. We could also, and I've done it, show the components. And we see that we have components perpendicular to the x-axis that are equal and opposite. and then equal components in the x direction. Because of the symmetry, these vectors are symmetric about the x-axis so that their x components are equal, and we could then just add the two x components. Now either way, that would have the effect, had we taken that into consideration, of eliminating the yj and the zk from the numerator of our integral. You can think about why that would be so, but we're not going to come back to this integral. It just shows that if we actually do this integral, everything you get from the j component, everything you get from the k component is going to cancel out and be zero. The only thing that's going to be non-zero is what you get from the I component. Okay. Now over here we're not going to think about this anymore. We're just going to develop the integral in terms of this picture. So what do we have? If we look at this circle, okay, this circle of radius r, this would be radius big R out here. We could postulate a circle of radius r star, and because of the symmetry, and I'm not going to go into minute detail in this argument, you want to think through it. Because of the symmetry, we could think of the contribution just from this ring, okay, a ring of thickness delta r and that would be like the thickness here. Okay, so we got this ring of thickness delta r of radius r star, and we want to find the field due to that ring. Well, the field due to this ring, every point is at equal distance from our point big X on the x-axis, and every point has an opposite point within the ring, so that, again, this idea that only the x component of our delta G is going to count. Taking this picture, we find that our r vector has magnitude big X minus little x squared plus r star squared. Here's our right triangle. Here's our, I've drawn that right triangle. I've drawn the right angle at the wrong point. Right angle is here, between the x-axis and the vector from this point to this point. Okay, and r is going to then be this side squared, well, square root of the magnitude of r. It's going to be the magnitude of this side squared plus the magnitude of this side squared, and then the square root. And clearly, if you think about it, that's what we're going to get here. That tells us then that the contribution delta G sub x for the whole ring is just going to be, and I left this off in class, and actually I'm going to pause for a second and put that in, so I'm going to fix that. Okay, I just fixed that, and it's just a temporary fix, and we'll go a little further into it on the next clip. I just put a delta V here because we don't have any volume. We didn't have any volume to multiply by the density, so we didn't get a mass. Okay, but now we got a mass here, and here's our expression. Now I'm kind of waving my hands at this point because I don't want to go into too much detail, and this is a detail, if you've had the vector calculus, you should be able to fill in easily enough. I've used the fact that the y and j components of the vectors that you get here all cancel out because of the symmetry that I mentioned before. If you got this point, then you've got this point, and this vector is going to be symmetric with this vector, and because of the argument we made here, that's all going to, the I and J components are going to cancel out. The J and K components are going to cancel out. We'll just be left with the I component, and that's what I've included here. I could make that much more rigorous, but we'd have to go through a bunch of pictures, and it's probably not necessary to get the idea of how we set up this expression. I'll also mention that the empty parenthesis here just contains this expression. I didn't have room to write it, but it should be clear what that expression should be.